We're interested. Oh, thank you. I completely forgot that. Was that you, Akio?
You're welcome.
Oh, thank you. Thank you. I should have started this that way. Well, I'm not going to repeat the introduction for you again, Ken. So those people that hear the recording will miss that important part of it. I'm sorry. Anyway, Ken, if you're ready, you are sharing your screen now, and you can take it off if you will.
Okay, great. Thank you, Kim. Just to, the Museum of EMC Antiquities is a bit of a grandiose name. It's my basement where I work, and it's full of antique radios and EMI receivers, things that were used clear back to the 1940s in our industry, as well as all the manuals that go with them and all kinds of books and handbooks going all the way back to that era. And it's a nice atmosphere in which to work. So that's the Museum of EMC Antiquities, and anybody who's traveling through Huntsville, Alabama, is more than welcome to contact me, and I'd be happy to show them around. So now, getting into the presentation here. So ARP-958 covers the calibration of antennas used at 1 meter separation from the test sample. This makes it a near-field measurement, which is key to much of what will follow. Examples of such use are CISPR 25, Mil Standard 461, and RTCA DL 160 for commercial aircraft. This presentation is about a problematical change in the subject revision to this half-century-old document. The proposed E revision requires separate horizontal and vertical antenna factor calibration for dipole-type antennas, like the biconical and the log periodic. The original release was in 1968 and covered only log spirals, so this wasn't an issue. Revision A in 1992 added other antennas commonly used in shield room tests, including the biconical, log periodic arrays, horns, and others. Revisions B, C, and D followed with minor changes. Draft E, with this new 2 antenna factor requirement, is another matter entirely. Note the Scarlet revision letter. Subtlety isn't our strong suit at EMC compliance. This, by the way, is the Liberty Labs antenna calibration facility in Iowa. It is now Keysight Liberty Labs. Keysight co-chaired the ARP-958E revision process along with ETS Lindgren. Beyond the pejorative meaning of dinosaurs over the hill and out of date, remember that dinosaurs were around for over 150 million years, much longer than mammals so far, and certainly mankind. Further, a big part of my career was researching the evolution of the EMC discipline before my time, mainly as applicable to vehicles. But we can all learn from those who went before us. So, if the chief consolation of old age is the ability to speak one's mind without fear of consequences, then I've finally arrived. If I don't upset someone in the audience today, I'm probably not getting my point across. I'm not here to make friends. I'm certainly not here to scare up business, but I am here to influence people. You need not agree with me today, although I hope you all eventually do. But I am here to plead a case, not simply inform, but present and persuade. Our discussion today is all based on well-known physics of antennas. There's no new information, no new discoveries, just basic antenna engineering principles that have been known since before many of these books were published. While this presentation is purely factual, from time to time an opinion based on facts will creep in. I will endeavor to point out when such an opinion is controversial. This doesn't mean the opinion is wrong, just that some misguided folks don't agree with me. If everyone agreed on this topic, there'd be no need for this presentation. Now, on the other hand, I seem to be the only person involved in the e-revision process who had a problem with what is going to be presented herein. I was first instructed to quit messaging on the topic, and then after the first 2 meeting invitations, no further invitations followed. My comments on the draft e-revision submitted through NASA's Marshall Space Flight Center were rejected. It is reasonable to assume I'm considered a crank by the balance of the committee membership. Keep that in mind as the presentation unfolds. Before we get into the details, some background material is pertinent. Antennas calibrated in the far field can be used to measure any far field signal and may be used interchangeably and at any far field distance, even though they are completely different in both kind and size. This is because both calibration and measurement are responses to plane wave illumination, and the only difference between such antennas is their response to the plane wave immersion. This is why nominal far field test methods such as CISPR-22 do not specify antenna type. Antennas calibrated in the near field are not interchangeable, and the calibration is only good for use at the actual calibration distance. This is because the calibration field is not plane, but has a wavefront unique to that antenna at that separation. When an antenna so calibrated is used to measure the field from a completely different source, say an EMI test setup in a shielded anechoic chamber, the resultant quote-unquote field intensity is relative to what the antenna picks up at 1 meter separation from an identical antenna. It is not a value that can be scaled with distance like a far field measurement. The quote-unquote field intensity so measured is only useful to the extent that the limit was based on that specific measurement, the measurement simulates the actual RFI problem the requirement attempts to control, and, most importantly, everyone does it the same way. This is why, for instance, MIL Standard 461 RE102 specifies antenna type and size, and why, my opinion, RTCA DO160 and CISPR-25 should follow suit. A 1 meter antenna factor is a convenient transfer function that resembles to some degree the response to the electric fields emanating from an EMI test setup, but there's no uncertainty bound on the difference. It is useful in the sense precisely as stated in the ARP-958 description, this slide on the next slide, but we could just as easily use the far field antenna factor, as long as we still made the measurement at 1 meter separation and as long as everyone reduced the data the same way. Shakespeare addressed this very phenomenon in Romeo and Juliet. A rose by any other name would smell as sweet. For some of you, this material is old hat. Some of you may have never given it much thought. In the backup slides, I have a heat flow analogy specially tailored to be of interest to vehicle EMC engineers. It's in backup because it will not be necessary for some. At the end of the presentation, if there's time and interest, I will go through the analogy to shed more light on the concept of a measurement where the results depend on how the measurement is made. Prior to 1964, EMI radiated emission limits were antenna-induced. That means the limit was expressed in terms of the voltage that would appear at the terminals of the antenna, rather than as a field intensity. This required specific antennas to be defined and used, typically the 41-inch rod antenna and the tuned dipole. These were placed 12 inches from the test setup boundary, vertically and horizontally, respectively, for rod and dipole. The term antenna factor in those days had a different meaning than today. It accounted for any impedance matching and/or balun losses between the antenna element or elements and the actual 50-ohm coaxial antenna terminal. It was simply a loss factor with units of dB. Antenna-induced limits made a lot of sense when the antenna was parked 12 inches from the test sample. It's fairly obvious that this is not a field intensity measurement, but borders on a crosstalk measurement, with capacitive and inductive coupling playing a role. When they backed antennas up to 1 meter separation in the mid to late 1960s, that was when they transitioned to a field intensity limit. An arbitrarily defined new antenna factor was tacked on in order to express the limit as a field intensity rather than an RF potential. Hence, the original 1968 release of ARP-958. But this change was still encumbered with all the caveats and limitations described for near-field measurements in the previous slides. In fact, the military is still making antenna-induced measurements, in that MIL Standard 461 prescribes the kind of antenna and its separation and orientation. And while the military maybe alone recognizes this, any radiated emission measurement made at 1 meter separation from a test setup longer than 1 meter is still a near-field measurement. My opinion, it might have been better to stay with antenna-induced limits. People wouldn't be making the kinds of mistakes we will be describing shortly. The purpose of ARP-958, as distinct from other typical far-field antenna calibration regimes, is for use when measuring a source 1 meter from the antenna. As a direct corollary, this standard cannot possibly provide for the accurate or absolute measurement of emissions from an unknown source whose dimensions exceed the separation distance. The best it can do is provide precise measurement by calibrating using an identical antenna that represents the distributed source at the same separation distance. Precise here means repeatable across various facilities. It's not that you can't hit the bullseye is undefined. The best that can be had is a small group. All test facilities get the same answer. So for the EMI measurement on the right, antenna terminal voltage adjusted for any cable loss, preamplifier gain, and then antenna factor is a value based on the response of the antenna to a particular field distribution unique to that antenna at a separation of 1 meter. That's shown at the upper left. Whereas stated in ARP 958 section 1.1, the transmit antenna simulates the actual distributed source to be measured. Further, compare in this case the 137 centimeter tip-to-tip length of the standard biconical with 2 meter or longer test setup boundaries. The simulation is, shall we say, inexact. We measure an artifact of the test setup. It is not a true field intensity that can be extrapolated based on distances in the far field. And this is just fine as long as we all agree to do it the same way and as long as it is a reasonable simulation of the type of interactions we expect on an integrated platform. And as long as we check that the EMI performance measured in the test facility provides EMC on the integrated platform. That is, we verify in a production or pre-production vehicle that all the RF systems operate compatibly and within specification. The theoretical construct of a plane wave is the curvature of a sphere with infinite radius. A practical description of the far field depends on the need for accuracy, but the criterion can be qualitatively described such that at the far field distance, the phase difference between waves emanating from any 2 points on the radiating structure is less than some arbitrary amount expressed as some fraction of a wavelength. For a theoretical plane wave, that phase difference is 0 wavelengths. For ordinary use, a phase difference not exceeding 1/16th wavelength is often used, resulting in the familiar far field boundary cited as twice the square of the maximum physical aperture dimension divided by wavelength. So you learn two things here if you haven't seen this before. 2d squared over lambda is not a physical constant, but a commonly accepted and useful construct. And also, this only works when d is large compared to lambda, else the second term we ignored can't be. By the way, for a tuned half-wave dipole, 2d squared over lambda is just equal to a half wavelength, which is a commonly used far field value for a tuned dipole. In the Freeze equation, notice as r goes to 0, the ratio on the right blows up. But conservation of energy says the ratio on the left cannot exceed unity. Therefore, the equation predicts that gain is not independent of antenna separation as that separation decreases. As r gets smaller, g decreases from its far field value. Conservation of energy yields an upper bound on what the gain can be as r approaches 0, but it does not predict the actual gain value. In the near field, the behavior of gain as a function of decreasing separation is a complex function of wavelength, separation, and antenna physical aperture. This is just one page of many involving calculations for a dish antenna. Bessel functions, anyone? The end result of several pages of complex mathematics plus numerical integration is this semi-log plot showing gain derating for various aperture type antennas as the separation from the antenna decreases from the far field boundary. Ordinate and abscissa are backwards from conventional use. Distance moving in from the far field is on the ordinate axis, with separation decreasing as we move up the axis. Fractional values are normalized relative to the far field distance, which has unity value, and is plotted on a logarithmic scale. The abscissa shows power density relative to power density at the far field point. It's graduated in dB relative to the power density at the far field point. Therefore, it has a value of 0 dB at the far field point. Point F is our origin, the far field point, from which we count both separation and change in power density. Curve A is for reference only and shows how power density would vary if it were calculated using the Freeze equation with gain independent of separation. It increases without bound. Curve B is not very interesting, but curve C shows the power density variations on axis for a uniformly illuminated horn antenna. And curve D shows power density variations on axis for an antenna aperture like a parabolic dish antenna with tapered illumination. It is apparent that near field gain decreases with separation and is a function of antenna type. These plots show 1, 3, and 10 meter antenna factors for commonly used EMI test antennas. Note that 3 and 10 meter antenna factors are closer to each other than to the 1 meter antenna factor. This is because as antenna separation increases, gain asymptotically converges on the far field value. The drawing on the left is the basic calibration setup and method in ARP-958 revisions A through E. The difference between the ratio of transmit to receive power is compared with antennas in place versus disconnecting the antennas and connecting the two cables together. That sets up the receive power versus transmit power ratio, zeroing out cable loss. The only difference between this and a far field gain calibration is A, separation, and B, the presence of a ground plane. The math is the same. And the intent on the left is to minimize reflections off the ground plane economically compared to the facility shown on the right, where cost has not been an object. In both cases, a measurement free of significant reflection error is the goal. Getting antenna factor from gain is a simple exercise in algebra, spelled out in every version of the ARP from 1968 forward. It relies on two assumptions. One, the received power at the antenna port is developed across a matched 50 ohm load, and two, the impedance of the field impinging on the antenna is that of free space, meaning a plane wave, meaning this is a far field calculation applied to a near field measurement. This is why near field gain is sometimes referred to as apparent gain. In light of the previous discussion, the CISPR 25 1995 text highlighted in red typeface is, my opinion, not just wrong, but fundamentally and embarrassingly so in such a high-profile standard. I can change my name to Fred Astaire, but it doesn't alter the fact that I can't dance. I could change my name to Bill Gates. My bank account will not swell. Lipstick on a pig. There are innumerable sayings about dressing something up to appear to be something it is not. Simply calling something a field strength limit instead of an antenna-induced limit does not make it a far field measurement. Now, back in 1995, the fact that CISPR 25 got this wrong was neither here nor there to someone primarily working aerospace EMC. Not my turf, not my problem. Some of you may, in fact, be wondering as I speak where this aerospace guy gets off wandering onto your turf and casting aspersions. Well, the answer to that is what's coming up has spilled over from the automotive world into the wider world, including aerospace and military EMC, via SAE ARP-958, which is used by all disciplines making 1 meter antenna separation measurements, and which started out supporting military EMI testing. The 2016 version of CISPR 25 has removed the errant text and recommends, but does not require, a standard set of antennas. This is a reasonable first step towards standardization that doesn't instantly obsolete many test facilities' existing antennas, but puts them on notice. So an improvement here, but a similar type error and a massive disappointment is coming up next. Based on this note, the SAE ARP-958E committee says that polarization-specific antenna factors are justified by popular demand. Aside from the, my opinion, really bad idea of polarization-specific antenna factors, note that this edition of CISPR 25 opens the door to different test facilities doing things in either of two different ways, contributing to lack of repeatability between test facilities. Not a good thing, especially in light of how much money is pumped into getting a CISPR 25 chamber just right. Now we're getting down to the issue at hand, for which the foregoing was just an introduction. Okay, we all know that in space, no one can hear you scream. And absent gravity, there's no up or down. Likewise, in the absence of any mass capable of causing gravity, there's no vertical or horizontal either. Vertical on Earth means aligned with the local gravitational field. Vertical and horizontal are not absolute descriptors, but relative to some frame of reference. So, far away from any frame of reference, there's no horizontal or vertical, and there can be only one orientation-independent antenna factor. If, pay attention, antenna factor is inherently orientation-independent, and yet there are indeed measured differences between orientations, then the difference is an artifact of the measurement itself. This means that the difference must be due to the presence of the reference, in our case, the ground plane. As noted, the far-field gain measurement at lower left goes to a lot of trouble to remove the ground plane as a source of perturbation. The ARP-958 calibration at center tries to minimize ground plane-induced perturbations, but in a more cost-effective manner. The EMI test setup at the lower right has the lower extremity of the vertical biconical antenna within 52 centimeters of the floor in the depicted military measurement, but within 32 centimeters of the floor in the CISPR 25 setup. If our antenna calibration routine minimizes the effect of the ground plane reference using a 3-meter separation from the ground plane, but our EMI radiated test method on the lower right does not, then what are we doing reducing EMI test data to account for the minor imperfections of the calibration site? ARP-958, since the A revision includes a ground plane, so two effects must be taken into account. The first is reflections off the ground plane, shown on this slide, and the second is capacitor loading on the next slide. Ray tracing math reveals that the bounced ray is about 16 dB down from the direct ray, and that this results in less than 2 dB change relative to no reflection. This isn't really a problem in the vertical polarization because when vertically oriented, antenna gain in the direction of the ground plane is much lower than broadside. Differential ground plane loading is an issue for wire-type antennas whose separation from the ground plane varies between vertical and horizontal polarization. For aperture-type antennas, this issue doesn't exist or is negligible due to symmetry. The next slide quotes section 4.1.1 of ARP-958E, saying that for vertical polarization, the ground plane effect is negligible, which implies that the degree of differential loading this far from the ground plane is acceptable, and that the major issue with the ground plane is reflections, which, as we noted, are going to be more of a factor with horizontal polarization. The blue typeface text is where SAE ARP-958E says the ground plane effects for vertical polarization are negligible, with calibration performed 3 meters above the ground plane. The problem in E is the new red text requirement for separate horizontal and vertical polarization antenna factors. As noted, these problems are associated with the presence of the ground plane. On the left is the situation for an SAE ARP-958 calibration 3 meters over a ground plane. On the right is a better simulation of the actual setup. One can see that if the correction factors are applied for reflections based on the 3-meter high calibration setup, they do not at all correct for the reflections encountered 1 or 1.2 meters over the floor. My opinion, it is essentially false advertising to claim otherwise. Note that in addition to the magnitudes of reflection amplitudes being quite different, so is the spectrum of reflection errors due to the different path lengths traveled. There will be reflection errors at lower frequencies 3 meters above the floor than at 1.2 meters above the floor. My opinion, if you're hell-bent on providing reflection corrections as a function of polarization, then it must be done at the actual height in test usage, not at a height picked purposely to minimize the quantity being corrected. On the left is the situation for an SAE ARP-958 calibration 3 meters over a ground plane. On the right is the actual situation during test. One can see that the correction factors are applied for differential capacitive loading based on the calibration setup. They do not at all correct for the differential capacitive loading encountered 1.2 meters over the floor. This is just a repeat of the last slide, but vertical polarization, not horizontal. Once again, in my opinion, it is false advertising to claim otherwise, and if it is somehow now essential to provide differential capacitive loading corrections as a function of polarization, then again it must be done at the actual height in test usage, not at a height picked purposely to minimize the differential loading. Note red text, citation, and date. The antenna factor as used will differ markedly from that calibrated. The citation is from the well-known 6-volume Don White EMC handbook series. Handbooks are not forums for advancing the state of the art, but collections of what is already known. In this case, 50 years ago, in 1971, we're not blazing a new trail here, folks. This entire slide is on the one hand factual, but controversial, so we'll say it's my opinion. Consider the train of logic or illogic presented so far. We must quantify something which cannot be quantified in an absolute sense because the measurement result depends on the tool we use to measure it. The best we can do is agree to a standard measurement so that we all get the same answer. To the result from this standard method, we add minor corrections based not on the measurement itself, but on the tool's calibration, which purposely minimizes effects that are present to a much higher degree in the measurement setup. It's bad enough to ignore the concept of significant digits. It's adding insult to injury to require a correction factor that doesn't represent the measurement itself, but only a minor imperfection of the tool's calibration site. In summation, if we as an engineering discipline wish to avoid what one colleague of mine calls the Rodney Dangerfield effect, i.e. EMC don't get no respect, it behooves us to have requirements and measurement protocols in accordance with the laws of physics and metrology. Now, my opinion, if it isn't already obvious, is that we are doing just fine with 3-meter height antenna factor calibrations. Nothing's broken here, nothing needs fixing. But purely as an exercise following this thought process to a logical conclusion, it is interesting to consider how ARP-958 might have been written differently in the first place if it had been written, say, post-2000 instead of in 1968. Instead of trying to get the antenna away from the floor to minimize errors from reflections, today we can economically make the floor go away. This wasn't practical for the typical EMI test facility in 1968 and was still expensive in 1992. But post-2000, at many EMI test houses, eliminating the floor and other complications could be done with existing test facilities. Pyramidal absorber isn't the best solution down to 30 megahertz. Ferrite tile works much better, both in terms of specified absorption, but also because pyramidal absorber only achieves specified absorption when the electromagnetic field pointing vector is parallel to the direction of the cones, which is certainly not the case for the floor bounds here. For this facility, the pyramidal absorber would have to be backed up with ferrite tile. Below 1 gigahertz, the floor would only need ferrite tile. Notice that with an absorber line chamber, there's no need for a mast to raise the antenna to 3-meter height. If an EMI test facility has a test chamber with ferrite back cones, antenna calibration could become a do-it-yourself proposition, which was the original intent back in 1968. But note that even if you don't have this high-end chamber, a ground plane laid down on a parking lot free of obstructions and some ferrite tile absorber would suffice. No cones necessary for the floor alone below 1 gigahertz. Maybe it's time to write a new SAE ARP-958E DIY. We've arrived at the end. Conclusions, all my opinions. Antenna factors should be measured in the complete absence of reflections and loading, or practically speaking, under conditions where the errors due to reflection and loading are controlled to an acceptable level. SAE ARP-958E is better with respect to not providing polarization-specific antenna factors. Maybe it's worth considering reducing those errors not by trying to inadequately quantify incorrectly measured differences, but by providing a calibration site that eliminates polarization-specific errors, and one that, not coincidentally, is part of many existing EMI test facilities. And that is it, except for my backup slides. I am open for any questions and hope to entertain some. Thank you.
Thank you, Ken. Please, anyone in the audience who wants to ask a question verbally, please unmute and go ahead and talk to Ken. Otherwise, put your question in the chat box and we will make sure that it gets answered.
Hey, this is Karen Burnham.
Hey, Karen.
Hey, how's it going?
I'm here.
You'd mentioned in earlier slides that there's a branch now in CISPR 25 where test houses can do things two ways. Could you make the connection between that and the implications of this EREV a little bit more explicit?
Well, yes. In CISPR 25, 2016, it says, that you should have both vertical and horizontal antenna factors. In 958E, it says that they're going to do both of those unless they're told otherwise. And also in the 2016, let me go back here to the actual words instead of trying to remember them. Let's see here. Yeah, here it is. So a single antenna factor in this, let's see here. The users of this standard are aware that antenna manufacturers can give independent antenna factors for horizontal and vertical polarizations. In this case, the appropriate antenna factors are used for measurement in each polarization, which means that if you had those, you would load in a separate horizontal and a separate vertical antenna factor in your antenna factor files on your machine, and then when you took the horizontal, it would be corrected for the horizontal and the vertical for the vertical. But then if you have a single antenna factor, in this case the antenna factor is used for measurements in both polarizations. So what this means is, to me anyway, and you can disagree, that some labs will do it with, some labs will use a single antenna factors, other will use different one, polarization specific ones, and to me then that contributes to unrepeatability between different test facilities.
Okay, gotcha. Thanks.
Any other questions? Hearing none, Ken, you want to go through your other materials there then?
Well, I guess that kind of depends on whether there's no questions because everybody's in violent agreement with everything I said, or they don't care, or they're just blowing it off. So, I mean, let me put it this way. Well, I'm going to share this one just because it's fun. This really doesn't bear directly on what we're talking about. And then I'll go through my backup example of a different kind of a measurement where the answer depends on your test equipment. But what I'll say is ahead of time, for anybody who's listened to what I've said so far and is going like, yeah, what's the big deal, or is blowing it off, they don't need to sit around for it. But if somebody wants to, kind of get down into the nitty gritty of what it means to have the results based on how you make the measurement, then that's fine. I didn't want to bore anybody with it. But one thing that comes up a lot that's different than what we talked about is that people who work in the CISPR 22 world, and actually CISPR 22 I think is obsolete, but I can't remember the name of the spec that replaced it. But what I'm talking about there is the people who make measurements at 3, 5, 10, even 30 meters, right? People whose work is kind of well, basically it's far field work. You know, they'll quibble and they'll come up with corrections, and I call those people the 10th of a dB people, because they get worried over stuff that we just don't even think about. But a lot of times those people will look at 1 meter measurements and say, you know, our repeatability or our uncertainty is so much better than yours, and you should do things our way. And this is kind of an example of what they call the streetlight effect. So I'm just leaving that cartoon is like, I don't know, probably 60 to 80 years old. I don't remember exactly how old it is, but that kind of reasoning has been around for a long time. And the point is, I remember, just as an example, a very long time ago, I think it was an electronic word processor, but not like Microsoft Word on a PC, but it was like a dedicated word processor. And that thing had an FCC sticker on it that said it had met, you know, Class B requirements. But if I had my phone, my wireless phone sitting next to it, you know, the thing that, you know, I think they operated around 900 megahertz, it was totally unusable sitting next to that. But if I moved it about 3 meters away, it worked great, right? So, but the point is that had that thing needed to work 1 meter away, that 3 meter qualification would not have sufficed. Even though it would have been a very, very accurate measurement, it would have been a worthless measurement. Just like, you know, if you've lost your car keys in a dark alley somewhere and you walk out to where there's a street light and look around for it, yeah, you can see better, but, you know, you're wasting your time. So that's just a fun one I use when I run across people like that. Okay, so here's an analogy, and this is not a mathematical analogy, but I think I don't know, I found it appealing. So near field, far field temperature measurement analogy. So in the far field, any antenna covering the desired frequency range and with desired sensitivity, gain, or antenna factor suffices. In the near field, the measurement result depends on the sensor used. So my analogy here is, you know, between the little spectrum analyzer and the antenna on the left, and that voltmeter and the thermocouple connected up to it on the right. And in fact, if you look at the math that you use to reduce the data, it's identical. Right? You measure a voltage and you adjust it for a transducer factor, and in one case you get volts per meter, in the other case you get a temperature. All right. Let's see. Anything else here? So in this analogy, well, let me back up. In this analogy, field intensity corresponds to temperature. The antenna corresponds to the thermocouple. The antenna factor corresponds to the thermocouple's temperature coefficient, and a spectrum analyzer or EMI receiver, which older terminology is frequency selective voltmeter, corresponds to the handheld voltmeter. So in a typical application as shown at left, any of the thermocouples usable in the desired frequency or desired temperature range will yield the same temperature measurement once the raw voltage output is adjusted for the temperature coefficient of the thermocouple pair. Depending on the temperature range, there are a large variety of standard models from which to choose. The unspoken assumption is valid as long as the thermal mass of the test sample is large with respect to that of the thermocouple itself, which is typically the case. But what happens when this assumption is not valid? An EED, or electroexplosive device, is a device that converts transient electrical energy into a contained explosion for various purposes. In a hot bridge wire EED, the conversion from electrical to explosive energy is achieved by running current through a thin conductor that acts as a fuse. That is, it heats up, melts, and ignites a surrounding powder pack, which explodes. Some examples of EED applications are airbag deployment, launching a missile, aircraft ejection seats, and the separation of launch vehicle stages. This latter uses explosive bolts. All these examples have three things in common. The function can only happen once, and once initiated, is irreversible. The function must ultra-reliably occur precisely when commanded, and the function must never occur unless commanded. These goals are achieved by designing a wide range between the bridge wire current that causes initiation and that which does not, characterized by the all-fire current and the no-fire current. In a typical such device, the all-fire current is 5 amps, and the no-fire current is 1 amp. That means that 1 amp can flow through the bridge wire continuously and not cause ignition. 5 amps will cause detonation immediately. Radio frequency induced current safety margins of either 16.5 or 20 dB are typically levied on such devices. These are aerospace type numbers. I don't know what you all use. What does that mean? It means that the amount of current in the bridge wire is either 16.5 dB down from, or 15% of, or 20 dB down from, 10% of, the no-fire current. With a 1 amp no-fire device, that means a maximum induced radio frequency current equivalent to either 150 milliamps or 100 milliamps of direct current. There are various ways to instrument that, but typically a 100 or 150 milliamp direct current is passed through the bridge wire and the resultant temperature rise is assessed. Then, when the integrated vehicle is exposed to the real or simulated electromagnetic environment, an instrumented bridge wire is monitored to verify the proper margin is obtained. One way to monitor the induced current is to measure the bridge wire's temperature rise with the powder pack removed. There are various ways to do this. Let's consider the use of a thermocouple. Attaching a thermocouple lead to the bridge wire increases its thermal mass significantly. Thus, for a given current passing through the bridge wire, more heat may actually be dissipated, but at a lower temperature. Attaching a thermocouple eliminates the possibility of measuring the true temperature rise in the bridge wire alone due to current passing through it. But a relative measurement is still possible. That is, we can measure the temperature rise due to the no-fire direct current, or 16.5 or 20 dB below the no-fire direct current, and then measure the temperature increase from any RF currents induced in the bridge wire. But notice that whereas in a measurement of the temperature of a large thermal mass, we can use any appropriate thermocouple, in the bridge wire case we cannot do that. With a thermocouple, once we have measured the temperature rise due to the direct current, we must measure the temperature rise due to any RF current with the exact same size and type of thermocouple in order that the attached thermal mass be identical to that when we set the limit. When we do this, we are not measuring the true temperature rise, but we are measuring an accurate ratio of the temperature increase due to RF versus direct current. It did not matter what thermocouple we chose for the DC measurement, but once we picked one, we're stuck with it. Also notice that we can totally dispense with the correction of the thermocouple potential to temperature. All we need is the measured thermocouple potential for the DC and RF cases. The thermocouple corresponds to the antenna, the voltmeter corresponds to the spectrum analyzer or EMI receiver, temperature corresponds to field intensity. In either case, we need neither once we have specified the correct transducer. The only real figure of merit is the induced potential at the transducer output. And that is it. That's my simple analogy for when a measurement, when the results of a measurement depend on how you instrument the measurement. Is there anybody left?
Oh, yes.
Okay. I mean, that's it if there aren't any questions. I would be very interested to know, and I don't need a real-time response here, but I mean, since there was only one question, I'm really curious to know what that means. Agreement, disagreement, don't care. To me, that Rodney Dangerfield slide, that's a big part of it. In other words, if we're doing stuff that looks stupid to the outside, it makes it much harder to do a good job, because people, essentially, if they don't respect the quality of work you're doing, then when you really need to get something done, it makes it much harder to get it done. Anyway, that's all I had, unless there's any more comments.
Kim,
So is your suggestion to have the standard prescribe only one calibration method so that if it's used as the standard, everybody's going to do the same thing?
Well, that everybody needs to do the same thing. I mean, even if I don't get my way, all right, even if, let's just say, everybody out there thinks that separate horizontal and vertical antenna factors are the cat's meow, then everybody needs to do it that way. I mean, you can't have some people doing it one way and some people just using a single antenna factor. But what I'm saying is that having those two separate antenna factors, first of all, is wrong. But then also, let's just say again that people think we need both of them. Then you need to measure them the way you're using them. I mean, the point was that if you're measuring 3 meters above the ground plane, which is for the whole purpose of minimizing bounce and loading, then what are you doing applying that correction factor when your antenna is only 1 meter above the floor, right? In other words, that is the false advertising. That's like we're taking account of these of reflections and loadings. Like, no, you're not. You're measuring them 3 meters above the floor. In fact, when you start in 1968 with ARP-958, the original, not Rev A, it didn't say anything about a ground plane, and it didn't say anything about a height above a ground plane. Right? You go to A, and they raise the thing up 3 meters, and they say you got to have a ground plane. Well, the purpose of that is to have a standard reflection, right? Which is a good thing. I mean, for a calibration, for calibration, you want a standard setup. But the point is that the reason they went to 3 meters was to minimize the very thing that now they're trying to correct for. But the correction is for 3 meter above the ground setup, and we make measurements 1 meter above the ground. So it's totally false advertising.
Hey, Ken, this is Arnie Nielsen calling.
Yes, sir.
Why are people objecting to this? It seems pretty straightforward what you're saying.
What I've heard is that, and I'm not probably the best advocate for the people who disagree with me, but the best that I've heard is that vertical and horizontal antenna factors are different, and we have to take account of that. Right? That's what I've heard. And by the way, sir, I've been looking for a real long time, and I don't know if you can help me, for the early either SAE or, in your case, Ford specs from back in the day, what kind of things they were doing, let's say in the late 60s and 70s for EMI testing, before we had CISPR 25, before we had ISO 11452-X. If you had any access to any of those, my emails on this presentation, I'd really appreciate being able to see some of that.
Well, I wrote the original Ford spec. I'm trying to figure out what year that was. It was in the late 70s, I think, early 80s.
That alone is good information. Yeah, if you happen to have something like that in your files, and I could get a copy of it, I would be much obliged.
Yeah, I'll send it to you. It was called what was it called? A 1316 spec.
Okay.
And EMC at Ford was me half-time and a technician. That was it.
Well, this is just since you're on here, I'd be very interested in your opinion, and this is unrelated to this presentation, but from I don't know from whenever they put the first AM radio on a car up till I don't know somewhere in the 1990s or later, the 41-inch rod antenna was the perfect simulation of the whips that you saw on every car, regardless of who made the car.
Yeah,
but
you're right.
At some point here now, everybody, I don't know. I guess the what do you call it? The cross section or the cross section of that whip in the wind is too much or something, and now we've got our antennas deposited as artwork on window glass, and I'm curious, as to how good of a simulation the rod antenna is anymore in the AM or, for that matter, FM bands.
It's not.
They use
It's not at all.
They use shark fins now. It's an active antenna you'll see in the top of cars. But so I seen
Well,
some,
I kind of assumed that the shark fin was more for your, higher frequency stuff, not the
No,
AM.
they put sometimes they put AM and FM in there as well.
Yeah.
By the way, my name is Michael Kirkhart. I test these very antennas. The big driver for this, and some people might laugh, but it's aesthetics. In a lot of cases, the dictates from the styling people are that they want no visible antennas. And that is why you don't see whips on the fenders. That's why you see, stuff that's in the back glass or in the shark fin or hidden in liftgate spoilers and all that kind of stuff. But I can tell you those antennas have nowhere near the gain performance of that whip on the fender. Not even close.
I mean, that's clear. In fact, and you can correct me if I'm wrong here, but I think that those really short antennas require a low noise amplifier in order to get a decent signal, right?
Yes,
But
just about every vehicle, anything that's not using a whip on the fender is an active antenna, and that brings its own interesting issue, shall we say?
Oh yeah, it's an EMC engineer. It's employment for EMC engineers. But the whole idea of design people driving things, and this is getting way off base here, but especially for Ford, if you think about Henry Ford, they can have it in any color they want as long as it's black. And now those people run things. And I mean, I remarked to my wife
they do.
many times that you cannot tell anymore what make or manufacture a car is unless you actually look at the emblem or the name, because they all look alike. So it's kind of like, why don't they just have one set of those guys for everybody, because they're not doing anything useful.
That'd be funny to bring up as a cost-saving measure.
Yeah, exactly. Just my opinion, though.
here's something else to think about. When I do a lot of consulting, and I always are coming across this thing of meeting spec or is it a real world problem? So I take a little radio. You can take these radios, they got signal to noise and signal strength right on the readouts. A lot of these radios use a chipset from Silicon Labs. And I'm thinking, taking something like that, a $50 radio, you can tell if it's a problem or not. And yet we're spending $50,000 to do all these chamber tests. There's got to be a simpler way to do this, you would think. If I can sort it out whether it's a problem or not with a $50 radio, that's kind of crazy, isn't it?
Well, I think a big part of it is, and I don't want to turn this into a CISPR 25 bashing fest, but a lot of work in recent years has been done by people supporting CISPR 25, where they've gone around and done round-robin tests between different facilities to see what kind of repeatability they have, right?
Yeah.
And sometimes they get pretty good, and sometimes they don't, what have you. But a lot of that goes into, I mean, these are really expensive chambers. I mean, if you compare what you guys do to make a room meet requirements versus a mill standard room, I mean, you guys are spending a bunch more money, which is understandable. There's good economic reasons for that. But you all can correct me if I'm wrong, but from what I've seen looking at the automotive industry, what's driving all of this is that the OEMs wield these specs pretty much like a whip, and the tier ones and the sub tiers, they basically, if they don't meet these requirements, the letter of law, they're not going to get a contract. They're not going to get these things bought. And so the repeatability between chambers is way more important, because the meeting the requirement is a barrier to market entry. Whereas, say, in the military and often even in the aerospace world, the contract has been let up front on the basis that you will meet such and such a requirement. And then when you actually get to running the test, that's after the contract has been let. So the fact that we don't have the repeatability between mill chambers and mill tests that the CISPR people want, that makes a certain amount of sense. So I don't think I don't think it's a technical issue nearly as much as it is a kind of almost like a contractual or business issue.
Yeah.
But the problem is that, like I say, in the case of this particular presentation, it's not my primary objection, but it's clear that this is going to result in people making measurements different ways, which is not the way you guys want to go.
Now,
Yeah.
one thing I was curious about, how much
let
of
me,
the, oh, sorry.
I have to depart. I want to make sure Akio is ready to take over for everybody and run the door prizes at the end. Are you there, Akio?
No.
Yeah, it took me. Yes,
Okay.
yes.
Okay, very good. And thank you, everyone. It's been very informative and interesting tonight. I have another meeting I have to drive to. All of a sudden, it's drive time for meetings. Thank you. Bye-bye.
Ken, do you have time for another question?
Oh, yeah.
And this might actually be going out to, as much the rest of the audience, but, so much of what I've seen in the automotive world, especially with CISPR testing, they reference back to CISPR 16, I thought, for a lot of their antenna calibrations. And I was just skimming through it.
But see, CISPR 16 antenna calibrations are all far field. For CISPR 25 and the 1 meter measurements, they rely on ARP-958.
Ah, gotcha. Okay. I was wondering where the disconnect was.
So if, Mr. Nielsen seemed to find what I said kind of intuitively obvious, and I'm glad to hear that. But if the rest of you all feel the same way, I'd strongly encourage you to get involved with CISPR 25 and get it fixed.
Well, at the very minimum, the leaving it up to the test house to do on how they want to do it is a problem.
Yep.
Have you heard of, Ken, have you heard of this 7637 spec? It's actually transients. And it's
No.
taken us 30 years to get the latest version corrected for basically the Ford transients, which are more realistic. So it's a, as you know, it's a heck of a long process.
Right. But I mean, at least nowadays, I mean, you have CISPR 25, 1995, and I probably missed out on several updates in between, but I think most of these things are on 5-year rotations now. I mean, and so, if there is an error, it doesn't need to sit there for 30 years if people recognize it.
Well, unfortunately, it does. And that one example I gave you is, again, it's off the subject of this meeting, but it has to do with automotive transients. So there's been these ISO transients out there for years that are totally unrealistic. And Ford came out with a more realistic way of doing it, which is in their spec, and they finally adopted it after, honest to God, I'm not exaggerating, it must be 30 years. It took that long to add it. Keep the old, but they added the new. So it's painful to get these things changed.
Yeah.
In the old days, the way we used to check out the reception is just, we had a chamber that we just put the car in and measure the voltage coming out of the antenna with and without the noise source. That's how it was done. We still do that.
Exactly. I mean, see, at that point, though, I mean, that's exactly analogous to what the military does at the platform level, right? But if that's the first place where you find the problem, well, now that's not where you want to find the problem. That's where you want to verify that everything's okay.
Yeah.
You want to find the problem in the widget before it got installed, in the vehicle.
Yeah, there was no module specs at that time, so that's what they did.
Well, you just didn't have any modules for the most part. I mean, there were very few things that would generate. Well, you had your sources of broadband noise, like your ignition system, but everybody learned how to fix that a long time ago. And I guess you'd have little things like, electric doors. I mean, electric electric windows and windshield wipers. You had a few sources of broadband, but yeah, you didn't have all the stuff that was going to be putting out a spectrum of narrowband radiation.
That's true.
Incidentally, just because it's a group of automotive people here, I was reading that Tesla had punted on AM reception on their vehicles. I guess the pulse width modulation that they used to run the motors, they just didn't feel like they either couldn't or didn't feel like it was worthwhile trying to suppress that to get AM reception, and just kind of, I don't know. I felt bad about that. I was just being an old guy. Probably a lot of people don't pay any attention to AM anymore, but you know, it made me wonder, if you think about the fact that when the first time they put a radio on a car, clear back probably in the 20s or the 30s, you know, then they figured out they had to suppress an ignition system, which of course is, you know, tens of kilovolts of broadband noise, and then they punted on it now with these electric cars. It just didn't seem right.
Yeah, that seems weird because I don't know why Tesla doesn't put an AM radio. The rest of the car manufacturers do.
Not all of them. You can see a trend on some like the European electric vehicles where they're dropping AM
Oh yeah.
because, and I'm sure it's just because of this, because they can't get rid of the noise from the drivetrain.
I think BMW would dropped it for one.
Yes, BMW, I believe, is the manufacturer I'm thinking of.
Isn't that something? Yeah, and then in Europe, you want AM for long wave and all that sort of thing.
Yep.
I don't know how they get rid of that.
Yeah, it's kind of sad that here's an era where every car manufacturer has boatloads of EMC engineers. And back
Well, no, not boatloads.
Not boatloads.
Ford has a handful. They're very effective, but there's not a lot of them.
Well, the point is that it's an established discipline, and yet at the time when they had to suppress ignition systems for the first time, everybody was there were no EMC engineers, not by training anyway. It's strictly, that was just tackling a problem that they hadn't had to worry about before.
Yep. Well, I'll show you the old Ford spec. I'll send that to you, Ken. It's called a 1316. I'm sure I can get your email here somewhere.
Yeah, hold on here. Let me, if nothing else, I'll go back to my cover page. Okay, let's see. Right there at the bottom of my dinosaur sheet, ken.javor@emccompliance.com. Even a phone number there if somebody needs to actually talk to me.
Okay, I'll send that to you.
Much obliged. I really appreciate you being here, sir.
Yeah, they're always fun.
Okay, anything else?
Can you hear me, Ken? This is Jim Woodyard.
Loud and clear, sir.
I am the Vice Chair for Awards, and I'd like to present to you our Speaker Award. We recognize your professional commitment to the education of our members with a Speaker Award, which includes a donation in your name to the IEEE EMC Society President's Memorial Scholarship Fund. Your name, topic, presentation, and donation may be viewed at the chapter's Speaker Award list on our website, along with a complete list of Speaker Awards since 2012, when we instituted this award. I will send you an electronic copy of the award letter, and in it there is a hot link. You'll see it. It's underlined Speaker Award list, which you can click on and go to the website and see the Speaker Awards along with yours. I want to thank you very much for your presentation, and I really enjoyed it. And now Akio will take over.
Thank you, sir.
Before Akio takes over, is it possible that you can forward this presentation over to Scott or whoever so it can be distributed to the rest of us?
I could probably do that, but I will need to like convert it into a PDF.
Okay, yeah, that'd probably be the
it's
best thing to do.
It's pretty large. Yeah, I can certainly do that and send it to Scott.
Yeah, I'd like to understand this a little more. I don't work, like I said, I don't work in EMC. I work as an RF validation engineer, which means, and part of that I'm testing antennas. So part of this, I understand what you're getting at, because this is one of the things I've always had this issue with, this trying to lump a very complex thing into the simple antenna factor is always kind of like made me feel a little weird. And I guess you can get away with it when you're in the far field, but when you're not, then it's like, yeah.
Yep.
So that's, and I'm sure there's other people here who would like to have a copy of this as well.
I will do that.
All right, thank you very much.
Well,
This was supposed to also have been recorded.
On the same subject, who was just talking there, what's the frequency range of those shark fin antennas?
Well, it depends. If some of them are just set up for like cell bands. So we're talking, they'll typically have like 2 antennas. There'll be one of them will operate just as an uplink. Will only. Let me say this again. 2 of them will operate. They can operate both of them in downlinks. So that's how you get your 2x2 MIMO on receive. But for the uplink, only one of them is active. So there'll be just like 2 passive elements in there, and typically there'll be a patch in there for GNSS and a patch for like STARS, meaning Sirius XM, if the vehicle's so equipped. Now, some of them actually have the AM FM element in them as well.
So it covers a pretty broad frequency range. Too bad we can't come up with a spec using something like that as the antenna.
Yeah,
you wouldn't get into all these issues.
Yeah, the problem is for that antenna is very, very electrically small. The element for FM is very, very electrically small, and
yeah, it doesn't matter. That's the purpose of the spec, is to prevent interference with that exact thing. So
right. Well, yeah, the thing is, I mostly, interference is one thing. The thing I have to deal with is like, I'm looking at antenna performance. So things like, what's its realized gain, and what kind of, what's its directivity. For an FM, for AM FM reception, you don't want directivity. You want something that's and it has an omnidirectional pattern, which, oh, by the way, that whip on the fender pretty much did.
Yeah.
But a lot of these other antennas, they have all kinds of very interesting antenna patterns, and occasionally you'll see nulls in the pattern in certain directions. It's interesting.
One of the really, and you haven't done anything here to improve my opinion of quote unquote design people. The design meaning in the automotive sense, the people who pay attention to how the sheet metal is bent as opposed to how the car works. But when you drive an electrically short antenna, which now makes you have to put a low noise amplifier between it and the radio, you're opening yourself up to overloading that amplifier at much lower levels than the radio would be overloaded, because the radio's intermediate frequency filter is protecting you from all the stuff, to some degree, protecting you from all the out-of-band stuff, but that low noise amp has to be wide open over whatever range that radio can be tuned, so you've lost all of that.
You see, you've identified one of the problems.
Oh yeah, that problem's been around for. That's a known problem, and the fact that that design people can force a design, an electrical design in that direction that's just really, really bad.
Yeah, some part of me actually thinks that it's not being done maliciously, but I believe that maybe there's folks that think that they can make these antennas small and invisible, and they'll still have the same performance. And
Yeah,
I think that's
I
really,
didn't
there's a
mean it
huge,
was-
there may be a disconnect there.
I didn't mean that it was malicious, but the process is broken when the people who are concerned about appearance and obviously don't know a volt from a watt can drive design decisions that impact this way.
Well, that's always been true. You got to sell cars.
Yeah.
Design
Yep.
takes precedence over everything. You got to sell them.
Yeah, unfortunately, yeah, that's kind of true. I mean, the cars get sold partly by their appearance, and maybe,
Partly,
you know, people will be
mostly.
irritated if their radios don't work the way they expect them to. And, you know, the one thing that's unfortunate is we don't have like a regulatory lever on this stuff like the cell phone people do. See, as much as you got the people that want to make the cell phones really nice and cute and all that kind of stuff, they still have to allow the antenna people to do what they need to do to get it to work. And because the big thing is, well, and aside from even just before, well, the customer might not be happy if their phone drops calls and all that kind of stuff, but there's specific requirements that the carriers put on the cell phone manufacturers, and they have to test for these things like total isotropic sensitivity, total radiated power and such. And if you don't pass the carrier's requirements, they will not allow your device on their network. And if they won't allow your device on your network, guess what? You can't sell it.
Right.
So they have that lever that we don't, even though their design, I give a lot hats off to the antenna engineers who do stuff for cell phones. I have no idea how they make any of that stuff work, especially with all the co-located radios and all that. It's, in my mind, it's kind of almost a miracle. But if in the automotive world we had some sort of a lever like that, maybe we could force some compromise.
Reality check here, guys. Jeopardy's coming up in 10 minutes, so let's
Sorry, I'm talking too much again.
All right. Well,
wrap it up.
thank you all.
Good
All right.
presentation. Thanks, Ken.
Any other questions? Okay, let me stop recording.